Good afternoon and welcome to COMM819 Infectious Disease Epidemiology. Last week, we discussed the sources and method of collection of epidemiologic data for infectious disease outbreak investigation. So today, we'll be discussing how epidemiologic studies are conducted in attempting to discover if a causal association exists between an exposure or risk factor and a health condition or outcome by using different epidemiological designs. Also, we will be looking at the various steps involved in conducting an outbreak investigation of an infectious diseases. So let's look at some of the learning outcome. Upon completion of this section, you will be able to 1. Describe the general dichotomies in epidemiological studies. 2. Distinguish between descriptive and analytic epidemiology. 3. Formulate a valid and epidemiological hypothesis. 4. Select and conduct appropriate experimental or observational studies. 5. Define your study population, sampling technique, and measures. Then 6. Recognize the types of experimental or observational study designs and how to select your exposure and control for a study. Then 8. Know when and how to calculate prevalence, odds ratio, or relative risks of exposure and measurement of impact of an association or attributable risks. Then finally, you should be able to describe and conduct an outbreak investigation of infectious disease. Okay, so now we're going to look at the general dichotomies or general considerations in epidemiological studies. Okay, so when designing an epidemiologic study, such as when assessing possible causal role of a risk factor for a specific disease, choices or considerations must be made about. Okay, you don't just go into the field and begin to say, I'm here to investigate outbreak. Understand? You need to make a prior planning. Okay, so there are certain considerations that you need to look at, very, very important. Okay, for example, you need to consider the purpose of the study. What kind of study do you intend to carry or conduct? Okay, and the role of the investigator, hypothesize effect of exposure to the population. Then what's your unit of analysis? Okay, is it on the community level or at individual level? Then selection of the appropriate study design for the study. You need to put that into consideration. Then defining your population of study. That has to be put into consideration. Then selecting the subject for the study. Then your sample size. What sample size is appropriate for an epidemiological study. Then your sampling technique, you need to look at that. How do you intend to collect your samples or data? Then summarizing the data, how do you intend to summarize the data? Then measure of disease frequency. What parameters did you collect and how do you go about measuring disease frequency? then measure of association, and how do you relate the risk factor to the disease outcome. Okay, so all these need to be put into consideration. So how each of these plays a role. So we look at them one at a time. Okay, let's look at the consideration number one. Like we said, purpose of the study. So for the purpose of the study here, we're going to ask the question: is it a descriptive or an analytic study? For descriptive study, usually it is qualitative in nature. It is usually the first part of a disease outbreak and investigation. Here it describes the distribution of the disease by time, place, and person. Then also it's used to generate hypotheses of disease causation or for health planning. An example of descriptive data include periodic survey of health status of maybe a community or individuals. Then knowledge, beliefs, attitude, practices, behavior, and environmental exposure to certain risk factors. All these are qualitative in nature, and data from descriptive studies they need to describe deeper the demographic before going into the analytical epidemiology. Then for the analytic or analytical epidemiology or studies, here it is the analysis of observation using suitable diagnostic and statistical procedures. It involves the systematic evaluation of suspected relationship, for example, between an exposure and a health outcome, and systematic evaluation of suspected relationship, for example, between an exposure and a health outcome. By exposure here, we mean independent variables. Some call it health determinant, some call it risk factors, and some call it causal agents. While the health outcome could be disease, no disease, and maybe death. Okay. Then the analytical study also measures and tests the association between a hypothesized risk factor, that is exposure, and a disease outcome. Okay, this is very important. Maybe you're going into a field, you want to investigate whether a risk factor, for instance, a risk factor, say smoking, whether smoking is associated with a particular disease outcome, say for instance, uh, coronary heart failure. Okay, so you need to first of all gather the descriptive data, then you subject it into analytical epidemiology, you follow all the steps, then based on the data you now test the hypothesis to see whether smoking actually expose one to coronary and heart failure. Okay, so this is what analytical does. So it measures and tests the association between a hypothesized risk factor. Like I said, the risk factor is the word causal agent or disease determinant, and a disease outcome. So that is the outcome of disease, which could be uh, based on the risk factor, the nature of the disease. For instance, mosquito bite is a risk factor to disease outcome, which is what? Malaria. Okay. So you could hypothesize whether mosquito bites is associated with malaria in a particular community. Okay, so here mosquito bite is our exposure, which is the risk factor, which is the vector, is the health determinant, while the disease outcome is the word malaria, which could result into death, no death, or no disease at all. Okay, then the analytical epidemiology can also be categorized into experimental or observational. Okay. Okay. So like I said in the previous slide, the analytical epidemiological study can be divided or categorized into uh, experimental or observational. So experimental, here we said according to the study design, the investigator manipulates the exposure of a participant to some factor. Okay, and this is very, very important. The keyword investigator manipulates. Okay, so in any experiment that you need to manipulate one factor in order to favor another or to see the effect on the other, you time it experimental. Once you are able to manipulate one of the factors, so such experiment are experimental. Then example clinical trials or community trials, where a particular treatment or preventive intervention is provided to a group of people and their subsequent experience is compared to that of people not provided the intervention. And all these are examples of such experimental. So sometimes experimental analytical epidemiology are also called intervention uh, study. Okay. Then for observational study, observational analytic epidemiologic study, here the investigator does not manipulate exposure of participants to risk factor. Most epidemiological studies are observational. Okay, the investigator, you don't have any power to manipulate. You just go to the field and just observe based on the natural happenings. Okay, you don't have the power to manipulate any of the factors. You just go out and observe what is happening and you take your data, you look at those that are exposed and you try to look at another place that are not exposed and you just take the data. Okay, you don't have the power to manipulate, just a natural happening. That's the difference between an observational and experimental. Example of observational include ecological studies, cross-sectional study, case control, cohort, which could be in retrospective or prospective. Okay, all these. So, but one of the very important ways to actually know whether an experiment or whether an epidemiological study is experimental or observational is that you must ask yourself this question. Uh, One is like, did you manipulate the exposure factor? Did you randomize any of the subjects? You understand? So once you can answer this, if you as the investigator actually do some randomization or manipulated some of the factor, then it should be all experimental. But if you uh, didn't randomize or manipulate any of the factor, you just went there, collected the data as it is, then it's observational. This is very important. Okay. All right. Let's go move to the. Okay. So our next consideration is to hypothesize the effect of exposure. Okay. So we said an epidemiologic hypothesis is a testable statement of a putative relationship between an exposure and disease outcome. And there are certain criteria for a testable epidemiological hypothesis. Okay, one, we said it must be clearly defined. Okay, so the hypothesis should clearly define your case definition. Should be clearly define the disease of interest. Okay, then it must be possible to prove that the hypothesis is true, and it must be possible to prove that the hypothesis is false. And the hypothesis must be supported by a literature, theory, and references. Okay, you don't just go and state a hypothesis that cannot be proven. For instance, we all know that based on literature that mosquito bite, there's a female anopheline mosquito bite transmit malaria, or we can say it's associated with uh, malaria, which is a hypothesis. Then you now state an hypothesis that states that dog bite, dog bite is associated with malaria. Can you prove that? So you can see that cannot be a scientific hypothesis because it's never in any literature or theory that dog bite can transmit malaria. We all know that dog bite is associated with maybe rabies, right? So for you to state a hypothesis, it must fulfill any of these particular criteria. Then the hypothesis should state the relationship between exposure and disease, whether it is harmful or beneficial. Harmful in the sense that the exposure increases risks or presence of a disease, and beneficial in the sense that the exposure reduces risks or presence of the disease. Okay, so that is for the hypothesized effect of exposure. Then unit of analysis. Another consideration, you have to know the unit of your analysis. Is it at individual level or at community level? Okay, at individual, that's person, animal is the unit of an analysis. Okay, or at community. Community deals with what? Population. It could be in a county, can be a local government or hospital. So you need to put this into consideration. Alright, and another consideration is the selection of an appropriate study design. We said the design of a study contributes to the strength of its findings. Okay, of course, a good study design will lead to a very good outcome. If your study design is faulty, then the overall result and discussion will be faulty. So this is very important. And below are some types of studies in order of increased strength for testing the relevant hypothesis. We have a case study or case report. Usually this is a single case describing one person with the condition as a case. Then we have case series where you have series of cases. Okay, then ecological study, and this deals with analysis of group of statistics. For example, comparing rates of disease between two countries, 2 or 3 countries. There is an ecologic study. Then cross-sectional study. This is usually a one-time study where you just go out to the field and you just collect the data without any follow-up. Okay, that is assessing individual at one time, such as survey. Then we have case control study. Case control study. You have the case and you have a control. You can see the case is the maybe those that come up with the particular disease. Then you have a control. those that don't. Then you try to compare whether that suspected exposure is actually the one influencing the presence of the disease in the cases. Okay, so here you say case control study, studying those with the condition versus those without. Then we now have advanced case control, usually for any outbreak investigation. Like now we have coronavirus, COVID-19. Okay, so COVID-19, maybe based on the exposure, you have people that have already come up with the disease. You have others that don't have the disease. So those will not be your control. Then those that are actually exposed to the risk factors of COVID-19 will not be your case. Okay. Then we come into that proper. Then we have the cohort study, following subject over time to study the initiation or the progression of a disease. Okay, you want to actually know when actually the disease started, or there's in the past, or progression of a condition that is from present to future. Okay, so this cohort study usually is very expensive and is the most advanced of all these studies. Is the most advanced, and usually it can be in retrospect. Okay, you want to backdate and see what actually happened, or prospect, from present to future. Okay, but the cross-sectional study and case control study, they are the most commonly used observational studies. So another important consideration for epidemiological study is you need to define your population, your study population. So based on this, we have different categories of study population. We have the target population. So the target population is the immediate population where the sample will be derived from and where inference from analysis will be made. Okay, then another type, we have the study population. The study population is the population from which study subjects, that is the cases and non-cases, are selected. Then we have the sample. The sample are subjects, the subject drawn from the study population, both exposed and non-exposed, that provide data to the study. Then we have the external population. The external population is the larger population other than the target population. Okay, to whom the investigator may wish to generalize the study result. So you need to know the distinction between external population and target population. Okay, this is the larger. For instance, you want to investigate a particular disease in Nigeria, and Nigeria has a population of over 270 million. So is it possible to sample 270 million people? Absolutely not. So Nigeria as a whole becomes our external population, but our target population, that is within the 270 million people, the particular maybe the particular disease you are interested in will not be your target population. Maybe the people that have developed that disease. Okay, so maybe your target population will be just individuals between 1 to 5 years. Okay, maybe for instance malaria usually is more prevalent in children within the age of 1 to 5. Okay, so they now become your target population. Okay, then within the target population you have your study population. So which means within the 1 to 5 years Maybe you may be interested in all males or all females, or only those with blood group A or AB. Okay, so you select your study population based on that. Then your sample. Okay, then you know how many people you're going to draw based on your case definition. Okay, so we come to the different sampling technique on how to come up with a representative sample that will represent the whole, so that at the end of the study, uh, you cannot infer the outcome into the larger external population. Okay, all right. So here we said selecting subjects for the study. How do you select your subjects for the study of interest? Here we said the population at risk should be susceptible to the disease, i.e., can develop the disease of interest. Okay, so it means whichever population your subject must be people at risk of developing the case definition. Okay, if you are trying to sample people maybe within a particular community that are exposed to chemical radiation or physical radiation, let's say at ABU main campus, you have to sample your subject from ABU main campus. You can't go to Kaduna State University and begin to sample. Okay, so you have to sample your subject from the location where the risk factor persists. Okay, then the criteria for inclusion into the study should be explicit. It has to be representative of the target population using a particular sampling technique so that the result can be inferred back to the external population. Okay, all right. Then another consideration is sample size for the study. Sample size for the study. Here we said the sample size should be large enough to allow for a valid statistical testing. Okay, the larger the sample size, the more valid is the study. The smaller the prevalence, the larger the sample size. Okay, so this is very important. For instance, when for you to come up with a sample size, you need to do sample size calculation for any epidemiological study. You don't just go and begin to randomly pick people. You need to do your calculation of sample size. And the sample size is usually based on the prevalence of a particular disease. But where a disease uh, just occur for the first time and you don't have a baseline prevalence within the location, then I think it's appropriate you just take 50%. Okay, you take 50% as your sampling reference. Okay, that is 0.5. Okay. All right. Here we'll be talking about the various sampling techniques. Okay. With the various sampling techniques, sampling is very, very important. Okay. You don't just go out, like we said, epidemiological studies are usually scientific in nature. Okay, they follow a systematic approach. So the sampling is very, very important on the type of study to be carried out. And one of such sampling is simple random sampling, or some call it probability sampling. Here we said the simple random sampling or probability sampling technique is a technique where each subject in the population has the same probability or the same chances of being selected into the study. Okay, so everybody has equal chance of being selected. Okay, there is no zero probability. Everybody has equal chance. Sometimes when you ask people, okay, how did you sample your subject? They will say they randomize. How? And they will just that's the end. You understand? So there are ways to randomize your population in order to come up with simple random sampling. You could randomize your population using Excel. Okay, as a randomization table. You can use it, do it using Excel. You can do it online. You understand? So it will randomize, and you now follow the table to select your subject based on the arrangement. Okay, so with that, there won't be anything like what bias. Okay, then we have another sampling technique that we call stratified sampling. Stratified sampling usually, this is where the you have a heterogeneous population. Okay, heterogeneous population, you see different characteristics, okay, in the larger population. So in order to reduce heterogeneity, you need to create a strata. Okay, a strata. For instance, maybe this is population of let me say population of maybe cattle. Okay, different breed, different intrinsic factors. Okay, so you need to now create a strata based on maybe management system. For instance, whether this is extensive, semi-intensive, and intensive. Okay, so whatever population from the general that will come here will be extensive management system. Then here will be semi-intensive. Then here will be intensive. Okay, then from the strata, you now begin to collect subpopulation, your sample from each of these stratum. Okay, so at the end of the day, you now have a representative sampling number or sample number that represent the overall. Okay, so this is stratified sampling, and it's usually very good sampling technique for field epidemiologists. Okay, then another sampling technique is a cluster sampling technique. Here, sampling procedure where clusters rather than individual units are first selected from a population, and the observation are made on all individual units in each cluster. Okay, this is straightforward. You sample based on cluster. You can see maybe within this particular population you have a cluster of people with similar characteristics. You sample from this. Another part of the study site, another cluster, you sample. Okay, there's a group of individuals at a point in time. Then systematic sampling. Systematic sampling occurs when we select our samples in a systemic manner. For example, you might select every 10th house on a street to participate in a household survey. Or in another simple form, you could sample, maybe it can be in a hospital. Then you may decide to say, okay, every nth member or every nth person that comes to the hospital will be your sampling, will be among your sampling subject. For instance, any third person or any second person that enters the hospital. So when the first person comes in, you ignore him. When the second maybe patient comes in, it becomes your sample. Fourth patient, sixth, eighth, 10th, 12th, until you get your target. Okay, That is systematic sampling. You could also say, okay, every 10% that walks into the clinic. So the first 9 people that come in, you ignore them. The 10th person will become your sample number one. The 20th person will become your sample number two. 30th sample number three. 40, 50, until you achieve or you reach your target. So that is a systematic sampling. Okay, every nth member. Then other form of sampling, we have the convenience sampling. This most accessible or amenable sampling unit are selected. Okay, with convenience. Okay, based on convenience, because there are some studies that it's not everybody that will want to partake or cooperate. Okay, so you, the investigator, may rather want to go to a place whereby it will be more convenient for you to sample people. Okay, so that is a convenience, but this is not very, it's a weak form of sampling. Purposive sampling, and the most desired sampling units are selected, okay, based on your own choice. Then given exposure variables or specific disease status, okay, then maybe you just sample based on your own desire. Okay, maybe for instance, you know that a particular disease is endemic to a particular part of a community, and based on that prior knowledge, you may decide to just go and sample there. Okay, then haphazard sampling. Sampling units are selected with no scheme or method. They are sampled haphazardly. Okay, irrespective of this is though it's a sampling technique, but very weak. Then we have the multi-stage sampling. The multi-stage sampling occurs when a combination of sampling methods are used. Okay, combine one or two. Okay, but the most three most efficient or in terms of strength, stratified, random, systemic, and some excellent cluster are very uh, strong once it has to do with epidemiological study. Alright, and other considerations like summarizing the data. Now you've gone out to the field and you've collected all the data. Okay, so you need to summarize your data. Okay, all the descriptive data you collected, qualitative, you need to summarize them with what? Descriptive on statistics. Okay, then measure of disease frequency, then measure of association. Okay, all these are important consideration. So for summarizing the data, we said data for a typical epidemiologic study may be summarized in a table comparing numbers of cases, that is those with the disease or condition, to non-cases in terms of their exposure to a risk factor or beneficial agent. And this can be summarized as shown in the below figure. Okay, so this is a 2 by 2 epidemiologic table. 2 by 2. We have case uh, in the column case, then we have non-cases in another column. Then we have the exposure in the row, exposed and not exposed. So this is 2 by 2. Okay, so a typical 2 by 2 epidemiologic table is usually presented like this. The particular case is the disease, then the control, which is the non-cases. Okay, then the exposure, that is the factor. Okay, the exposure, that is the environmental hazard, it could be the hazard, it could be the disease agent. Okay, those are exposed to it. Then you now have another subject, those that are not exposed. Okay, so based on those that are exposed, how many of them develop the disease, the case, which is your A? Then how many of them do not develop the disease, which is your B? Okay, then for the not exposed, which is your control group, how many of them develop that disease and how many did not develop the disease, which is your D? So you have A, B, C, D. So for this column, we have total cases for the exposed and the non-exposed, okay, that eventually develop that disease will now be your total cases. Then for the non-cases, table the total here, okay. Then you may also want to total it row wise, that is case plus non-case, okay. That is for the total exposed and total non-exposed along the row, across the row, okay. And then here total. So this is a 2 by 2 table. So this 2 by 2, we use it and the subsequent slides to see how we can do a lot of things with this table, okay. So one of the things that information that can be deciphered from this particular table is measure of disease frequency. Measure of disease frequency. So we have disease prevalence by exposure status, and we have exposure prevalence by disease status. They are two different things, okay? Take note. So disease prevalence by exposure status is for exposed, those have been exposed, the prevalence is A over A plus B. A plus B is our total exposed. A is our exposed, right? So for exposed is exposed all over total exposed. Do you get it? A over total, that's A plus B, okay? Then for not exposed, it will be C all over C plus D, okay? So that is how to calculate the disease prevalence for the exposed and for the not exposed. Then to calculate the exposure prevalence by disease status, that's we're looking at it column wise, okay. This around you're looking at this because the case here is the disease, okay. So we are looking at exposure prevalence by disease status, so we are looking at it column wise. So for cases, it will be A all over A plus C, that is total cases, okay. Then for non-cases, it will be B all over B plus D, non-cases. All right. Then another consideration that we can, another important measures that we can deduce from this table is measure of association. So now we want to associate the exposure to the what outcome, whether the association is strong or weak, okay. So here, based on this calculation, you compute the exposure odds of exposure among cases and non-cases, okay. Then now for cases, odd of exposure among cases is A over C. Among cases, okay, the odd of exposure is A divided by C, okay, exposed over not exposed. Then the odd of exposure among non-cases will now be exposed over not exposed, whereas B divided by D. Okay. Then now, once you calculated the odds for exposure and non-exposure, you now determine the exposure odd ratio. Okay. Here you just calculated odds of exposure, but here you need to determine the exposure odds ratio. Okay, odds ratio of cases and non-cases. So the odds ratio of exposure, uh, usually written as E. E here stands for exposure. O odd and R ratio. Exposure odd ratio will now be A over C divided by B over D. Okay, that is simply odd of exposure among cases divided by odds of exposure among non-cases. Simple as that. Then this simplifies after cross multiplication to, if you cross multiply this, you get this A times D divided by B times C. But the simplest way to do it again is to cross multiply directly from the table. If you want to calculate the odd ratio, okay, then it will be for cases A to be this way, A times D divided by C. Okay, so once you do this, A times D, AD over BC, that will give you the odd ratio. Okay. Okay, now let's look at the last consideration, which is the study outcome. And here we said, based on the calculated exposure odd ratio, we can interpret the results and accept or reject the null hypothesis. So the first consideration, if your calculated exposure odd ratio is less than 1, then you infer that exposure is not associated with case, which means the exposure could be protective or beneficial. Hence, we accept the null hypothesis. Okay, remember our null hypothesis is always in the null form, that is negative form. For instance, you say cigarette smoking is not associated with lung cancer, but after subjecting your data and you are now able to calculate your odd ratio and you find out that it's less than 1, you can see here you have to accept your null if it's less than 1, because that was what you earlier stated, that it's not associated. But if it's greater than 1, it means it's possibly associated with lung cancer. Then you have to reject the null and accept the alternate. Okay. So another consideration, if the exposed odd ratio is equal to 1, it means the exposure has no effect on disease outcome. Hence, we reject the null hypothesis. Then here, if the exposure odd ratio is greater than 1, and the exposure is possibly associated with disease outcome, that is, the risk is greater in exposed cases or exposed individuals. Hence, we reject the null hypothesis and accept the alternate. So those are all the considerations for epidemiological study. So now, having understood the power considerations for epidemiologic studies, we will now cover the types of analytic and epidemiologic study proper. So I urge you to stay calm, and the business has just got started. All right. So from here, I will be a little bit faster because it's just what we have discussed in our previous slides. Okay. So here we are looking at we look into experimental study design. Remember I said experimental study design and observational study are two of the commonly used and analytic epidemiological study design. So here we look at them proper. Although in an epidemiological study, most of the studies are observational, but there's need to still understand how experimental are conducted. Okay. So this is equally very important. So let's look at some experimental study design and how they are used. So for the experimental study design, we said according to the study design, the investigator has the power to manipulate the exposure of participants to some factors during intervention. Okay, like that is exactly what we stated earlier. And this experimental study design can be categorized into a laboratory experiment or field experiment. So this distinction between the two is that in the case of lab experiment, it is generally artificial in nature. Okay, artificial, you have to control the temperature, you control things, you induce the disease, you understand. So it has a kind of an artificial low realism, you understand. It's not real, there's artificiality in it, you get it. Unlike the field experiment, it's more natural. Okay, there's high realism or realism. Okay, it's natural. There you have many factors that one cannot control, like temperature, both the abiotic and biotic factors. Okay, so the field experiment is more natural as compared to the lab. You need to control everything. Then in the lab, there are few and extraneous variables. Okay, you collect just few variables because many variables are controlled. Okay, why in field you collect as many variables as possible. Okay, then lab experiment is characterized by high control. Okay, because it's under a controlled environment. Why field environment you can't control other external factors. Okay, so usually the control is low. Then generally laboratory experiment you don't need to spend much, and usually they operate at low cost, though not all. Okay, you're going into molecular study there, you need to look at genome. Lab experiment can be very expensive, but generally they are of low cost. Then in comparison to field, high cost. Okay, you need to cost of traveling, cost of employing ad hoc staff. You understand? So it operate at high cost. Then lab experiment mostly they are of short duration. So within weeks, can be done within weeks, days. Okay, while field experiment mostly they entail long duration. Okay, so this is basically some of the distinction between lab and field analytic study. So here we said types of experimental analytic study design. Okay, generally experimental study design can be of the following types. We have post-test only design. We have pre-test, post-test design. Okay, pre-test, post-test design. We have factorial design. We have complete randomized design, CRD. We have complete randomized block design, CRBD. Okay, we have crossover design, and we have controlled trials. So all these 7 are types of what experimental study designs. So let's discuss them one after the other quickly. Okay, for the post-test only design, post as after, okay, post-test, after test design. So here we said it has two randomly assigned groups. We have the experimental group and a control group. Then neither group is pre-tested before the implementation of the treatment. Neither group is pre-tested. Okay, there's nothing like baseline data, okay, before the implementation of the treatment. Then treatment is applied to the experimental group, and the post-test is carried out on both groups to assess the effect of the treatment or manipulation. And this type of design is common when it is not possible to pre-test the subjects. Structure-wise, we have the participant group. Then we have the comparison group. This is our control, and this is our intervention. So for this, initially they were not pre-tested. No any data was taken. Okay, so the participants were given intervention, maybe a particular treatment. Okay, they were given intervention while the comparison group were given nothing. Okay, so you now follow up your subjects, then you now collect your maybe parameters, that is post-test. Then for the comparison group that you didn't give intervention, you also collect the same parameters, then you compare. Okay, so this is post-test and intervention. Okay, so the second type of the experimental analytic experimental research is pre-test, post-test only design. Pre-test, that is before testing, you give intervention, you took maybe baseline data, then post-test, after intervention, collect data. Okay, so here the subjects are randomly assigned to either the experimental or the control group. They are randomly assigned to either experimental or control group. Then both groups are pre-tested for the independent variable. Okay, remember I said the independent variable is usually the disease determinant or the exposure. Okay, but here it could also be treatment. Then the experimental group receives the treatment. Okay, and both groups are post-tested to examine the effect of manipulating the independent variable on the dependent variable. Okay, in simple chart, you have program participants. Okay, this is the experimental group and this is the comparison group. So before intervention, both groups were pre-tested. You took their baseline data. It could be, for instance, you're trying to treat diabetes. Okay, so using a particular drug, and you have a group of individuals that have diabetes, and another comparison group still with diabetes. Okay, but you decided to take their blood glucose level at the onset. Then this particular group, you decided to give them intervention, particular treatment. Then this other comparison group, you allow them be no intervention. So after, say for instance, 7 days or 2 weeks, you now collected their blood parameters, their blood, to measure blood glucose level. Okay, then you compare between the intervention group and the non-intervention group to see whether the intervention was actually effective or not. Okay, so this is pre-test, post-test experiment. Okay, so we have another experimental analytical is the factorial design. Factorial design. Here, the researcher manipulates two or more independent variables, which are our factors, simultaneously to observe their effects on the dependent variable. Okay, you have two independent variables, okay, or factors or determinants to observe their effect on the dependent variable. This design allows for testing of two or more hypotheses in a single project. Okay, that's one of the advantage. An example: researcher 4 different protocols for burn wounds with the frequency of the care being administered at 2, 4, and 6 hours increment. Okay, so when you put this together, you have 4 different protocols. Okay, treatment A, B, C, and D, and looking at them at different time at 2, 4. So all this is time. Okay, time. So you may put it in 3 level 1, 2, 3. So this is 4 by 3 simple factorial, 4 treatment by 4 by 3. Okay, so cell 1, 2, 3 will receive treatment A. 4, 5, 6, it goes like that. Okay, so this is a simple 4 by 3 factorial design. It could be made complex. Okay, and complex in the sense that within A you have various sub-treatment, maybe different doses of A, then another different level or treatment at the various level for B. So this is a simple one. It could be made complex. Okay, so here I'm just giving you the general description. Okay, for the purpose of calculation, I think there's another course, there's research methodology, epidemiological research methodology, which I am very sure in that particular course you'll be taught how to do all these calculation. But this is just to give you the basic knowledge so that you understand. Okay, so I don't want to go deep into the calculation aspect because there's another course that would actually take care of all this. Okay, uh, okay, completely randomized design, CRD. Okay, so for CRD, you say this is the simplest design for comparative experiment. The treatment are allocated to the experimental units or plots in a completely randomized manner. It may be used for single or multifactorial experiment. Okay, mostly CRD. Mostly this is one that mostly you see people say one-way analysis of variance. Okay, so here this is a simple structural representation. For instance, you have your sample population. Say for instance you have 100 and 128 rabbits. Okay, so you randomly assign them into 4 groups, group 1, 2, 3, 4, of how many? 32 rabbits each. Okay, then for group 1 you give them ibuprofen high. Group 2, ibuprofen high. Treatment 3, you give them a placebo low. Treatment 4, placebo low. Okay, placebo is just a form of control. Maybe the same substance but is devoid of the active ingredient contained. Okay, maybe a normal saline. So it's a form of treatment. So you now compare the percentage surface covered by this. Okay, so this is a simple CRD. You have 128, you group them into 4. Based on the 4, you may decide to give the 4 different treatment of the same substance, different level. Then you now compare using one-way analysis of variance. Okay, because this is a homogeneous sample. All right, and the more complex form of the CRA is the randomized block design. Okay, and we say here this design is used when there are inherent differences between subjects and possible differences in experimental conditions. If there are a large number of experimental groups, the randomized block design may be used to bring some homogeneity to each group. Okay, so usually where you have hetero, the sample have sorry, if there are a large number of experimental group, the randomized block design may be used to bring some homogeneity to each group. And this is a simple method for reducing the variability among treatment group. Okay, so this is just a simple you make the arrangement. This is your sampling population. Maybe you have 1,200 people. Okay, and you decide to split them into 2 groups, 600 men, 600 women. Then you now randomly assign them into group of 2 subgroup. Then under group 1 you have 300 men, group 2 another 300. Then for the female you also subdivide them into 2 groups of 300 each. So for the first group you give them treatment 1, maybe 325 milligram of drug. Then treatment 2, for men you give them just normal placebo. Then for the women, treatment 1, you also give them 325 milligram of a particular drug. Then the group 2, you give them placebo. Then now you compare the drop in temperature in all men and compare the drop in temperature in women. So you can represent it in a block form. Okay, maybe you have group 1, 2, 3, 4. Okay, 5, 6, 7, 8, 9, 10, 11, 12. All right, so and you have treatment A, B, C, and D. So based on your randomized block design, under your block 1, the first group will be given treatment B. Okay, you randomize the treatment. You mustn't follow A, B, C, D. So that's how randomization works. Group 1 can take any of the treatment. Okay, so in this case for block 1 you have treatment B being the first to go to group 1, treatment A, D, and C. Then in block 2, okay, you have treatment D going to group 5, treatment C going to 6, and up to block 3 you have different. In block 3 you have treatment D still going to group 9. Okay, but the good thing is that when you look at the blocking, like all like subject in group 1, group 8 and group 10 all received what treatment B, but they are all blocked, so that when there are inherent or differences, okay, whatever is happening to group 1 should be compared with what is happening to group 8 and group 10. Okay, then if you look at group 2, received treatment A, group 7 treatment A, and group 12. So it means group 12, 7, and 2 all receive the same treatment. Okay, so by doing it, arranging this way, the randomized block design may be used to bring some homogeneity to each group. Okay, all right. So another type of experimental analytic design is crossover design. Okay, crossover. Then here the subject in this design are exposed to more than one treatment, and the subject are randomly assigned to different orders of the treatment. Okay, like this is your population. Then the first you randomly allocate them into intervention, under study, and control intervention. Okay, so for those under intervention, under study, you first give them the intervention, then you now follow up by control intervention. You check the result. Then for this other group, you first give them the control intervention, then you follow it up by the intervention under study. Okay, just like here for the intervention, you are giving them Panadol extra. Okay, to see the effect of Panadol extra. Then the control, you give them normal Panadol. Okay, so in crossover, you first give the intervention Panadol extra, then followed by normal Panadol to now see the effect. Then for the other group, you give them the normal Panadol, then you follow by the word Panadol extra to now, then you compare the effect. Okay, follow up and compare the effect. Then the final or last of the experimental analytical study research is the controlled trial. For the controlled trial, assign or randomization of the exposure by the study protocol. Mostly these are of 3 types. We have the clinical trial, which apply to treatment for illnesses, e.g. chemotherapeutic trial. Okay, then we have the field trial, which apply to preventive intervention to maybe individual, example vaccine trial. Then we have the community trial, which apply to a group of individual intervention. Okay, for instance, fluoridation of public water compared with another community that uh, fluorine is not added to their water to now see the outcome. Okay, so clinical, field trial, and community trial are all additional types of controlled trial. Okay, and a distinction between field trial and clinical trial quickly is field trial mostly is done in healthy population. Okay, while clinical is done on individual patient. Okay, then field trial are often prophylactic in nature, while clinical trial are often of therapeutic. okay, including prevention of sequelae, okay, nice follow-up. Then field trial relies on natural challenge, while clinical trial no challenge, okay. And finally, field trial is for primary prevention, while clinical trial is for secondary and tertiary prevention, okay. So here you just stages of clinical trial from lab studies that take several years, which usually you term it preclinical, okay. Then it goes into phase one of trial, for instance vaccine development, okay. Phase one, there's human safety, which usually takes days or weeks. Then it goes into phase two, phase two, which is expanded safety, and it could be in weeks or months to actually ensure that it is safe. Then efficacy and safety usually takes several years. There is the phase three, okay, to ascertain its effectiveness and safety, okay, before it is eventually released to the public. Okay, so this is the general stages of clinical trial of any maybe intervention, whether be it vaccine or drug. Okay, all right. So, and a very important question to always ask is, why do we need a control for any form of type of an experiment? We need control, of course, because one, conditions often improve without active intervention. Okay, there are many reasons for this. Some diseases or some ailments, without even any intervention, they just go. You understand? So to actually decipher or confirm that it is the intervention that's actually carrying out the effect, we need to have a control. Okay, and this is because of some certain reasons. And one of such reasons is we have the placebo effect. Here, when you have a positive effect because of an innate intervention, okay, innate, that means a placebo is just an intervention that is devoid of an active ingredient, okay. So sometimes you just give a control group a placebo and it turns back to normal. You understand? So to actually ascertain that the drug of intervention or whatever intervention you're having, you need to compare with a control group that has placebo. Then we have the Hawthorne effect, which is usually a positive effect because of observation. Okay, you keep observing and without any intervention, something will bounce back. Then natural improvement in condition over time. Okay, maybe this may be due to immune status of the person. uh Without any intervention, person will bounce back to normal. Okay, so sometimes you won't be able to actually tell whether it is the intervention that actually make the person to heal or just in the natural occurrence. So that's why you need to have a control to always compare your result. Then it means the use of a proper control group to serve as a baseline for comparison will help neutralize these effects. Okay, so when you have a control group to always serve as a baseline for comparison, and this will neutralize all these three effects: placebo, Hawthorne, and natural improvement. Is very, very important to have control in all studies, whether observational or experimental. Okay, that's why in the case control, case called, you always have case and control. Okay, so it's very, very important, whatever type of study. All right. So, haven't looked at all the of experimental analytic study design. Now let's look at the other type, which is the observational analytic study design. Here, for the observational, the investigator does not manipulate exposure of participants to risk factors. Okay, you say most epidemiological studies are observational in nature. Okay, all right. So types of observational study design include case study or case report, case series, ecological studies, cross-sectional studies, case control studies, and cohort studies. Yeah, I've said this earlier. Okay, so now let's look at them one after the other, because now these are the studies that are most relevant to public health practitioner. Like I said, most epidemiological studies are observational. So please pay attention so that you get to understand this better. All right. So for the case report, you said a study of one diseased individual, typically an uncommon disease or set of symptoms. Okay. The study design will not require any comparison. Here, you don't need to compare with any. It's just a case report. Okay. Mostly, when you read a journal paper like review or case report, case definition, you just see a single report trying to give a description of the disease. Okay, at time, by time, person, and place. Okay, so mostly this is descriptive in nature. Okay, then we now have the case series. The case series, we said, a study of multiple occurrences of unusual cases that have similar characteristics. Okay, here the investigator can calculate the frequency of symptoms or characteristics among the cases. Neither a case study nor a case series would include a comparison group. Okay, so these two type of observation are the weakest of the overall observational studies. Okay, because they lack a comparison group. Therefore, ecological study, we said a study in which at least one variable, either an exposure or the outcome, is measured at the group level. The occurrence of disease is compared between groups that have different level of an exposure, which affords this study design to have at least one comparison group. At least one comparison group, which means it can have several comparison group. Okay, then an example of group level measure include the prevalence of hypertension among a specific population from different races. Okay, and this is one of the favorite case study or example of ecological, where they try to associate hypertension prevalence by different countries. And the hypothesis was that the prevalence of hypertension was higher in black, okay, in black races than white. And this was postulated, I think, in the US. Okay, they observed that the US black, usually the rate of and the prevalence of hypertension is higher when you compare with US white. You can see this is US white, okay, and this is US black. So in order to test the hypothesis, whether the hypothesis was actually right, because they base it on it may be probably due to a genetic factor. They observed that hypertension is always higher in US black. So they decided to now carry out an ecological study comparing different countries based on races, okay, on race. So Nigeria is inclusive, US white. The United States was divided into US white and US black. Then Canada, Jamaica, okay, and Sweden, Italy, England, Germany. So after collecting all the data, they now compare the prevalence, and they now observe that in Nigerian that is black, the prevalence of hypertension is very low, okay, as compared to US black. Then Jamaica as well. Jamaica that has African, let's say African origin, okay, also the prevalence tend to be lower in comparison to even the US white, okay. So based on this, they now rejected the hypothesis that genetics has nothing to do have nothing to do with what hypertension prevalence, okay, based on this observation. So this is a kind of ecological study comparing different countries based on certain maybe risk factor. Here they use race, okay. So this is a typical example of ecological study. So another, okay, one of the commonly used observational study is cross-sectional study or prevalence study, okay. So a cross-sectional study, here the population is sampled, okay. You define the population, and you define the population. The population you define will be both people that are exposed and non-exposed. You can see those in red are those exposed and those that are not exposed to a particular case definition. Then you further uh, subdivide your population into exposed and non-exposed, maybe to a certain disease factor, okay. So these are the exposed and these are the non-exposed, which is your control. Then you now follow up those that are exposed to see whether some will develop the disease and others may not develop it. Then you follow those that are not exposed to see those that will develop. So under this exposed, you can see about 1, 2, 3, 4, 5, 6, 7 people develop the disease, while under the non-exposed, only 2 develop. Okay, so using a 2 by 2 table that we discussed earlier, okay, 2 by 2 table, you can see this is the disease, which is our case definition. This is the non-disease, then exposed and not exposed. So remember our A, B, C, D. Okay, so since this is a prevalence study, remember one of the objectives I said how and when to use prevalence, odds ratio, and relative prevalence, right? All right, so for cross-sectional study, since it's a prevalence study, all you need is to calculate the prevalence, okay? So how do you calculate the prevalence? For those that are exposed, you calculate total number exposed. So how many of them came down with the disease, which is A, over total subjects that were used. That's A plus B. Okay. Then for the non-exposed, how many people were actually selected for the study? There is the total. Then how many came down with the disease? 2. Okay. So just simply 2 over total 1, 2, 3, 4, 5, 6, 7 to give you the prevalence in this. Then for the exposed, the prevalence will also be how many people were used. 1, 2, 3, 4, 5, 6, 7. How many came down with disease? 1, 2, 3, 4, 5, 6. Okay, this was not So number of diseased over total number exposed will give you the prevalence. It's a proportion. You may decide to multiply it by 100 to get the prevalence. Then you compare the prevalence in those exposed and those not exposed. Okay, so you will now be able to attribute that suspected risk factor, whether it's actually the causer of that particular image. A typical example here is, though not infectious disease, we are talking of here rabies and diabetes. Okay, so we're trying to compare whether obesity is associated with diabetes. Okay, so based on the prevalence study, you observe that uh, those are obese usually have higher prevalence of diabetes in comparison to non-obese individuals. But to actually test whether this hypothesis is true, you have to collect random sample from the same location. Okay, so here we have number of obese people. We collected 40,305 people. The non-obese 154,700. So out of the obese, how many came down with diabetes? 6,490. Then out of the non-obese, we have 8,915 came down with diabetes. So to calculate the prevalence of obesity in the obese individual, it will be those with diabetes 6,490 divided by total number examined, which will give 16%. While for the non-obese, total number of people that came down with obesity, which is 8,915, divided by total number of people enrolled for non-obese, which is 154,700. Okay, so you have 5.7. So you can see the prevalence of diabetes is higher in those that are obese as compared to those that are non-obese. Okay, so now you can comfortably or objectively say that obesity is highly prevalent. Obesity is highly associated with diabetes. But to actually come up with that association, you have to do what we call prevalence odds ratio. Okay, prevalence odds ratio will give you the degree of association. So simply is prevalence in obese divided by prevalence in non-obese. So it will be 16 divided by 5.7 and it will almost be 3. So that number 3, based on those criteria that I gave you, that if odds ratio is greater than 1, that means there is a strong positive association, right? So when you say 16 prevalence odds ratio, there is 16 prevalence in obese divided by prevalence in non-obese is about 2.9, which is approximately 3, which is greater than 1. That means you can now comfortably or confidently say that obesity is highly associated with diabetes. Obesity is the risk factor here. Diabetes is the disease outcome. Okay? Alright. Alright. Next observational study is case control study. For case control studies, or some people call it case comparison study, so these are studies where a group of individuals with a specific disease condition known as cases are selected for comparison with another group of individuals in which the disease is absent, which is our control. Okay, we are talking of disease. That's why the case control. The case here is the disease. Okay, it means the disease has all established. All right. So it's very important so that when we come to cohort, you don't get confused. Okay. So here we said case control studies are good for investigating outbreaks and studying rare and common diseases or outcomes. The approach for a case control study is straightforward. You start with cases of disease. Okay, you start with cases of disease as a first group. So cases are those that have diseases, that disease of interest. Then you now create a control group. The control group will be people from the same study location without the disease. Okay, then you now expose those cases to the risk factor. Okay, you expose them, and another group you don't expose. Then the control, you also expose the control here, and another group you don't expose. Okay, so the outcome of a case control study is odds ratio. You try to compare the odd of being exposed, cases exposed over odd of exposed control. Okay, so okay, and this is what I was trying to say. I said the outcome of case control study is odds ratio. You calculate the odds ratio. Unlike in the cross-sectional study that we calculated prevalence, for case control, it is odds ratio to associate the exposure and the outcome. Okay, so the table, this is a 2 by 2 table for calculating odds ratio. You have your disease, which is your cases, non-disease, there is your control, and exposed and unexposed. So this is the number of exposed for disease cases, number of exposed for non-disease cases, then unexposed C, then non-disease cases under unexposed D. So remember I said simple cross multiplication will give you the odds ratio, that is A, simply A times D divided by C times B should give you our odds ratio. But if you want to do it the longer way, you don't want to follow the shortcut, then you may calculate them individually. Like the odds of exposure in cases will be cases with exposure, which is A, divided by cases without exposure, which is our C. Then you also calculate the odds of exposure in control. Control with exposure B divided by control without exposure D. So once you calculate the odd of exposure in cases and odd of exposure in control, then you calculate the odds ratio. The odds ratio is simply the odds of exposure in cases divided by odds of exposure in control. This gives you A over C over all divided by B over D. If you cross multiply, you go back to AD over CB, AD over or CB or BC, which is our odds ratio. Okay, then this is a hypothetical example. We said to investigate if drinking alcohol is associated with liver cirrhosis. Okay, so for the case your population study, you have your cases, people that have developed liver cirrhosis, then your control. There are people that are under certain trauma bed, under hospital, they do not have liver cirrhosis. Okay, so under this, the exposure now is risk factor is heavy alcohol drinkers and low alcohol drinkers. to see which of these, whether heavy or low, is associated with any of these. So out of this, you calculate your odd of exposure in cases, which is 80/20. Then odd of exposure in control, which is 40/60. Then you now calculate the odd ratio. That is, when you do normal simple cross multiplication, it will be 80 times 60 divided by 20 times 40, which is this. You get your odd ratio as 6.0. So what's the implication of this value, 6.0? Remember the table I gave earlier for interpretation of odd ratio. If odd ratio is greater than 1, okay, we say that the association is higher, okay, that constitutes a risk factor. If odd ratio is equal to 1, it means the exposure does not affect the disease outcome. Then if odd ratio is less than 1, it means that exposure, rather than being harmful, it will be beneficial. That's protective factor, okay? So but with this, our odd ratio is highly greater than what? 1. So what will be the interpretation of this? It means is associated with higher odd of what? Disease, which means heavy alcohol drinking is what? You can put it this way. You can say the odd or risk of developing liver cirrhosis is 6 times higher in heavy alcohol drinkers than in low drinkers. That's just the interpretation. Okay? Hope you understand. It's simple. All right. All right. Our next observational study, which is the last and the most efficient but rarely used, because it is one of the most expensive, okay, is the cohort study design. Okay, the word cohort simply means our study population. Individuals is the cohort. Okay, we said a cohort study, a study that begins with persons who do not have the disease but with a known level of exposure to a putative risk factor. Okay, so your subject, they don't have the disease. Unlike in the case definition or case control, the subject, the case, they have already established the disease. But in the case of cohort, the disease is not there. But based on your previous knowledge that, okay, certain group of people have been exposed to certain factor that is capable of causing so disease in future. You understand? So you want to now test whether the people will eventually develop that disease based on the previous exposure. Okay? So that's cohort study. So it's a study that begins with persons who do not have the disease, but with a known level of exposure to the putative risk factor. The study sample is drawn only from individuals at risk of developing the disease or outcome. Then individuals are followed through time until some of them develop the disease. Okay, it's just a typical example is maybe people that stay under these telecommunication marks. Okay, we know that usually physical radiation from all these telecommunication marks are associated with cancer. Okay, so you now decide to visit a particular community, which you know that most of their dwellings are around area with telecommunication marks, and based on the radiation emanating from those marks, you may now hypothesize that, okay, these people are likely to develop maybe cancer due to presence of telecommunication marks. So it means people within that area are already exposed, okay? But none of them have developed cancer as at the time of carrying out your study, okay? So you now want to look at it, okay, if I sample maybe 20 people from this particular area that already have the risk factors, okay, they're exposed to the risk factors or a hazard, then you now sample another group of people within that same location that are not exposed or do not dwell under telecommunication marks. Then you follow them over maybe a long period, say 5, 10 years, to see whether the people that dwell under telecommunication marks will eventually develop cancer in comparison to the people that do not dwell under communication marks. Okay, so that is just a simple example. So for core study, you define the study population. Your study population should be people with no disease at all from the beginning, but you divide them into those that are exposed to that factor or hazard and those that are unexposed. Then you follow them over time to see whether those that are exposed eventually develop the disease or no disease. While those that are unexposed, also you follow them over the same time to see whether any of them will actually develop the disease or no disease. Then you now compare the relative risks of developing that, or the relative risks or incidence. In the case of core study, because there was no disease at the beginning, and you are anticipating that in future the disease will come up. So now we'll be talking of incidence of what disease, not prevalence. Okay, so you now look at incidence of disease. There is new cases. You compare the incidence of that disease in the exposed group to that in the unexposed. Okay, so here we talk of incidence ratio. When you compare the incidence in the exposed over incidence in unexposed, then based on that, you now interpret your result, just like in odds ratio. If the relative incidence is greater than 1, then it means that telecommunication marks is highly associated with a particular form of cancer. You understand? But if it's less than 1, it means telecommunication marks is kind of protective. Instead of harmful, you say it's beneficial. If it's equal to 1, then it has nothing to do with cancer. Okay, so the most important thing of core study is you follow it over time. Okay, yeah. So example of a core study here is example is to investigate the study hypothesis, that is whether smoking behavior may lead to heart disease. Whether it may lead to heart disease. It means from the beginning it has not occurred. Due to history of, okay, this is a risk factor, you want to see whether people that smoke will eventually develop heart disease in the future. Okay, so you have the study population, those that are exposed to smoking, those are non-disease as a control. Exposure is the keyword here. This particular set of guys they are known to be smokers, while these those that didn't develop maybe those smokers. Okay, then unexposed 4, 9. So just like the case of old ratio. Okay, so here we are talking of relative risks. Remember, in cross-sectional study we talk of prevalence. In case control we talk of old ratio. Then in the case of cohort we'll be talking of relative risks. There is the risk of developing something you are anticipating it will happen or it will occur. You talk of relative risks. Okay, not old ratio. So relative risks of developing heart disease if you are a smoker will be so you calculate the incidence for each. Okay, like incidence for this will be for exposed, it will be number of people that are exposed that have developed the disease, which is 4, over total number of people that are enrolled, which is what, 7. Okay, so it will be 4 over 7. Then the incidence uh, of heart disease in non-smokers, which is the control, will be those that came up with heart disease, which is 4 over total number that enrolled for the study, which is 13. So you have 4 over 13. So when you do simple cross multiplication, you get 0.57 over 0.31, and your relative risk is 1.84. The relative risk is instead of saying 1.84%, you may just multiply by 100 to give you 18.4%. Okay, so once you get 18.4%, then you should also note the interpretation. Okay, so based on this, we say when relative risk is less than 1, the exposure is not associated with case disease. That means exposure could be protective. When relative risk is 1, exposure has no effect on disease. If it's greater than 1, exposure is positively associated with disease, just like that of odd ratio. But in this case, we are using relative risk, not odd ratio. Okay. So now, based on this value, 1.84, we know that exposure, this is greater than 1. Exposure is positively associated with disease outcome. That means smoking, okay, is positively associated with heart disease. Okay, but in epidemiological term, instead of just leaving this as 1.84, you could just multiply by 100 and it will give you 18.4%. So to now interpret 18.4, you could just say the relative risks or likelihood, of developing heart disease among smokers is 18 times higher in smokers than non-smokers. Okay, the relative risks of developing heart disease is 18 times higher in smokers than non-smokers. So that is the interpretation. Alright, so we said core study may be classified into 2: prospective cohort study and retrospective cohort study. So let's look at the two. We say for prospective cohort study, usually some call it longitudinal study, follow-up, or incident study. Okay, so here persons without the disease are followed up to see who developed it in later time. Okay, and disease incidence in persons with a characteristics risk factor is compared with incidence in persons without characteristic factor. Okay, so in simple terms, we are trying to uh, it starts in the present and you're trying to see what happened in the future. That is prospective. Okay. You recruit your cohort, you classify participants as exposed or non-exposed. Okay. Then you now follow up the individuals to see who developed the disease. Okay. Then you determine the risk, relative risk or risk ratio. Okay. Relative risk, just like we calculated in the previous slide. So this is for prospective study. Then okay, then the other type is retrospective cohort study. This is also called historical cohort, non-concurrent and concurrent and cohort study. Then this one is based on history. You are going from past to present. Okay, you want to see what was the actual exposure in the past. It could be in the past 10 years to present. Okay, so that is it. A lot of students, not even students alone, even colleagues, you understand, they make a lot of mistake in most epidemiological study. You see somebody reporting that a retrospective study, the study was kind of done in retrospective. It's not true. For retrospective study, you must follow up. You understand? You must follow up. Somebody will just go to hospital. Somebody may just do a cross-sectional study survey and maybe goes to hospital, collect maybe record for past 10 years and will now come and report that he did a retrospective study. That is not a retrospective study. For any retrospective study, you need to follow up the subjects. You understand? You follow them up and study them over time. You're just going to hospital to say, okay, collected record for the past 10 years, and you now come and do analysis that is a retrospective study. It's not. It's just a normal survey. It's just a normal cross-sectional. It's not retrospective. Okay. So I've read a lot of paper that people misuse the word retrospective. Okay. Just to share with you, so you can see from past to present, that is, your cohort is your subject. You recruit based on a historical cohort. Maybe they've been once exposed to a particular maybe hazard. Then based on that, you follow up the individuals. Then you don't see whether the incidents exposed or the incident is not exposed. Then you determine the relative risks. Okay, the difference between this and the perspective is that, while the other one is from present trying to follow up a study that may take 5-10 years in future to see whether the people will come up with disease. For retrospective, you are starting from the present and going into the past to actually determine the cause of a certain phenomena. Okay, it's just like the uh, this simple this Japan Yokoshima and this bomb blast. Sorry, I can't recall it. I'm somehow exhausted. But all right. So that's for the retrospective cohort study. All right, so now let's look at the second topic, which is etiologic outbreak investigation. This is another form of advanced case control study design, but I will just quickly go through it. It's straightforward. So we need to understand some of the goals or method of outbreak investigation. We said outbreak investigation have both diagnostic and directed action components. And the objective of investigation may include, we said one, to assess the range and extent of the outbreak, okay, to reduce the number of cases associated with the outbreak by identifying and eliminating the source of the problem, okay. So you also need to identify new disease syndromes, to identify new causes of known disease syndromes, and to assess the efficacy of currently employed prevention strategies. Then one of the objectives again is to address liability concerns, to train epidemiologists, and to provide for good public relations and educate the public. So all these are some of the objectives of the investigation, outbreak investigation. Okay. All right. To successfully conduct any type of epidemiological outbreak investigation, Evans in 1982 offers or propose or recommend some helpful actions. Here he gave about 8 actions or steps to conduct an epidemiological investigation. And one of this is you need to define the problem. That's like the case definition. You need to define what problem are you trying to investigate. You need to confirm the diagnosis, whether the problem actually exists, and show that an outbreak has truly occurred. Okay. Then 2, we need to describe the outbreak clinically based on signs, symptoms, and tests. Okay, and epidemiologically based on person, place, and time. Okay, so if you are describing a disease, you need to tell us based on the signs, symptoms, and the various diagnostics that have been carried out in the community. You need epidemiologically to tell us the persons involved, the place and time variables. Then you need to also discuss possible means of transmission of that particular factor. Then calculate the rate of infection, diseases, and death. You need to formulate hypotheses about causes, source of infection, method of contamination and spread, and possible control mechanisms. Okay. Then number 6, you need to test causal hypotheses with epidemiologic, laboratory, and environmental investigations. Then finally, you need to draw conclusions and devise practical control solutions. Okay, sorry, the numbering somehow haphazard. Okay, so this is the these are some of the steps postulated or recommended by Evans 1982. So let's look at the other step as recommended by Center of Disease Control, CDC. Okay, the CDC in 1992 prescribed some investigatory steps for outbreak investigation, and according to their prescription, or one, you need to prepare for field work. Okay, establish the existence of an outbreak. You need to confirm, just like in Evans, you have to establish that an outbreak actually occurs. You verify diagnosis of cases. You need to establish a case definition. search for additional cases. Okay, and you need to conduct descriptive epidemiologic studies. Like, you need to tell us about the disease in time, place, and person. Tell us the clinical symptoms, signs, and details that have been carried out. Then you need to develop a hypothesis, a valid hypothesis. Then you evaluate the hypothesis. Then, as necessary, reconsider or refine the hypothesis and conduct additional studies. If eventually at the end of the day the hypothesis didn't actually answer the question, then you need to review, refine, and conduct additional studies. Then you implement control and prevention measures in order to either minimize or eliminate the disease. Then you communicate your findings to the people that actually reported the case. You need to give them feedback. Okay, so these are the simple 10 steps involved in investigation studies. I don't need to go into detail about that, because even from the outline is easy to uh, understand. All right. Okay, please try to take this revision question serious. This is just to justify your level of understanding of all that you've done in module 1. Okay, so take them serious. All right. All right. You could on your own practice all these questions and based on all that we've done. If you have any challenges, we discuss it on the WhatsApp platform or on the LMS platform. So feel free to ask whenever you have any challenge, and I'll try my best to discuss it on the platform. Okay, so these are virtually all that we've covered in module 1. So please try to study them. All right. All right. Our next interactive discussion will be on module 2. So, given your background, what you've done in module 1, I don't think we have just most of this will just be repetition. We've talked about transmission pathways, infectious diseases, okay, routes of transmission. We said oral fecal, arthropod or bone transmission. Arthropod is mostly insects. Then vector borne, yes, the insect and other maybe an active passive vector. Then we have contact or sexually transmitted infectious diseases. We have foodborne transmitted infectious diseases, mostly maybe by pathogen like bacteria. So I think this module 2 is just a walkover. It's just a walkover. I think it shouldn't be a big deal. Please read ahead. Kindly read ahead. Okay. All right. We discuss it on the platform. All right. All right. Thank you for your patience, and stay safe and keep healthy. See you next week. All right. Stay safe. Cheers. Thank you.